Good afternoon, students.
Good afternoon, ma'am.
Good afternoon, ma'am.
So, in yesterday's lecture, we have seen stability of fixed points. We have seen theorem also. First, we have seen some definitions. Stable fixed point. V is said to be a fixed point. V is said to be stable if given any ball B of V epsilon, there is a ball V delta, so that if U belongs to BV delta, then F raised to T at U belongs to BV epsilon. Means the points near to V does not wander far from V under all iterations of F. Otherwise, it is said to be unstable. And asymptotically stable fixed point means it should be first stable fixed point, and then it requires additional condition. Additional condition means all solutions which starts near to V converge to V as t tends to infinity. Then we say that it is a asymptotically stable fixed point. Similar definition will be applied to periodic point. So if W be a periodic point of period k, then W is said to be stable if W, f of W, f raised to k minus 1 of W are stable as fixed points of f raised to k. Similarly for asymptotically stable. Then we have seen this theorem 4.17. If f has a continuous first order derivative, then if mod of f dash of v is strictly less than 1, then v is asymptotically stable, and if it is strictly greater than 1, then v is unstable. Means to check stability of fixed point, we require this theorem. Means this theorem will be useful. We have seen some examples also. We have seen stability of fixed points of some functions, and I given some examples also for homework. Okay, so now we will start today. We will start a Liapunov function, which will be also useful for checking stability of a fixed point. So let's start lecture 45. Liapunov function. So first we will define what is Liapunov function. Liapunov function. Liapunov is a mathematician, and the name has been given to that function as Liapunov function. So what is that? Let small v be a fixed point of f. A real valued function, real valued continuous function, in fact real valued vu capital, we will denote it by capital V at u, defined for all u in Rn is called a Liapunov function for f at v, small v, provided that capital V at V is equal to 0 and V at U is not equal to, instead of not equal to 0, it is rather strictly greater than 0. V at U is strictly greater than 0 for U is not equal to V. Whenever U is not equal to V, capital V at U is strictly greater than 0. And there is a ball V about V, so that this delta difference of V at U, and it is approximately where they are defining as V at F at U minus V at U. This must be less than or equal to 0 for all U belongs to B. Okay, so what is, let V small v be a fixed point of F, a real valued function Vu. What is domain and codomain of F? What is domain and codomain of F? F is a function from Rn to Rn. Okay, Rn. And what is V? Capital V. V is a function from, it is a real valued function Vu, defined for all U belongs to Rn. So what is the domain? What is the domain for V there? Capital V?
Rn.
Rn, yes. Rn. And what is codomain? It is a
Rn.
real valued function. Means R. Okay. So this capital V is called as a Liapunov function for F at V, provided that this capital V at V is equal to 0. Means that function vanishes at that fixed point, and at remaining points it is strictly greater than 0. V at U is strictly greater than 0 whenever U is not equal to V. And also additional condition, there exists a ball B about V, means there exists a ball centered at V, so that of some, maybe of some radius R. Okay, so that this delta T of Vu. One second. Delta T, this difference which we are defining approximately as V at Fu minus Vu, this must be less than or equal to 0 for all U belongs to B. So if my function V satisfies this condition, then that will be called as Liapunov function. Okay, so this function will be called as Liapunov function for F. Means if such function exists, then we will say it is a Liapunov function for F. Is that okay?
Yes,
we will see in examples
Yes,
of Liapunov function. This is just definition. And if this above inequality is strict inequality for U not equal to V, then V is called as strict Liapunov function. Okay, so if the above inequality is strict means here it is less than or equal to 0. So if it is strict less than 0 for all U belongs to B, if there exists such ball for V at F at U minus V at U is strict less than 0 for all U belongs to B, then we say that it is a strict Liapunov function. Strict for U not equal to V, then capital V is called a strict Liapunov function. Liapunov function for f. Strict Liapunov function for f. So let U be a solution of equation, say U at t plus 1 is equal to f of ut with U at 0 belongs to B. Then the inequality sorry. Then the inequality, this delta t V at u, which we are defining as V at f at u minus V at u is less than or equal to 0, requires that V at ut be non-increasing as a function of t as long as ut belongs to V. And when f is continuous, the existence of a Liapunov function at V implies that V is stable. So whenever we want to check stability of solutions of this equation, u at t plus 1, we'll write this properly, u at t plus 1 is equal to f of ut with u at 0 belongs to B, then the inequality, this inequality requires that Liapunov function be a non-increasing as a function of t, because we are saying it is less than or equal to 0, this function, as long as ut belongs to B. So when f is continuous, the existence of a Liapunov function at V implies that V is stable. So whenever we need to check whether fixed point V is stable, if we can find some Liapunov function at V, then we can say that it is stable, otherwise it will be unstable. So we will write this thing in a theorem. We will state this in the form of theorem. Theorem 4.18. Let V be a fixed point What is meant by a fixed point? Let V be a fixed point of f means what? F at V is equal to
F of
V.
V is equal to C.
Yeah. And assume that f is continuous on some ball about V. If there is a Liapunov function for f at V, then V is stable. V is stable. And if there exists a strict Liapunov function, then we say that V is asymptotically stable. If there is a strict Liapunov function for f at v, then that v is said to be not said to be, it will be like definition, then v is asymptotically, then v is asymptotically stable. So if we want to check whether it is asymptotically stable or not, we have to show the existence of strict Liapunov function there. And if only Liapunov function exists with that inequality is less than or equal to, then that v will be just stable. Okay, so this theorem we will state without proof, because its theorem requires its proof is more analytical and it is a big theorem, so we will skip proof of this theorem. Just we will use this theorem to check the stability, and we will use the statement of this theorem and corollary as well. So we will after this theorem we will have one corollary of this theorem that will be also useful. Corollary 4.1. Suppose that there is a strict Liapunov function for f at v, so that what is that delta v at u, this is nothing but v at fu minus v at u less than 0 holds for all u belongs to v and f is continuous on v, then every solution of equation u at t plus 1 is equal to f of ut that remains in b for t greater than equal to t0 must converge to v. Small v. So theorem 4.18 says that if v be a fixed point and f is continuous on small v, and if there exists a Liapunov function, then v is stable. And if there exists a strict Liapunov function, then v is asymptotically stable. So what this corollary says that if there is a strict Liapunov function, then every solution of this equation, which equation? This u at t plus 1 is equal to f of ut that remains in b or that starts in b must converge to v. That follows from asymptotic, because asymptotically stable means what? All solutions which starts near to v should converge to v. So theorem 4.18 implies corollary this 4.1. Is that okay? So whenever we want to show that solutions of this equation converge to v, then we will show existence of a strict Liapunov function at that fixed point. Okay. Now we will have corollary 4.2. For this proof means it follows from definition of asymptotically stable. Corollary 4.2. Suppose V is a fixed point for F, and B is a ball about that fixed point. I mean center is fixed point, so that mod of Fu minus V is strictly less than mod of U minus V for U belongs to B, whenever U is not equal to V. Then also every solution of the equation, the same equation, U at t plus 1 is equal to f of ut, that originates in B must converge to V. Again, the corollary 4.2 follows from the theorem 4.18. Because V is a fixed point, again mod of Fu minus V is strictly less than mod of U minus V. Then every solution which originates in B must converge to V because it is asymptotically stable. So we will have examples based on this Liapunov function. Take first example. Use theorem 4.18 to show that the origin is stable for the equation U at t plus 1 is equal to f of ut. F of ut is given by here cos theta sin theta minus sin theta cos theta, and ut. So we have already shown, for this example we have already shown origin is stable. How we have shown? We have calculated the eigenvalues of this matrix, right? This is like equation 4.4. U at t plus 1 is equal to a times ut, where a is this matrix cos theta sin theta minus sin theta cos theta, and we have found its eigenvalues, and we have shown its modulus of that eigenvalues is strictly less than 1. And then we have shown the origin is stable, right? So now here we have to use theorem 4.18, means we have to use Liapunov. We have to show there exists a Liapunov function, and based on that we can say that origin is stable. Okay. Can you recall this? Recall that stability was established already by computing eigenvalues, of the matrix. So now we will use we will try to show there exists a Liapunov function. So first we will define a function and we will show that it is a Liapunov function. So here we define V on R2 by V at U. Since it belongs to R2 means vector is U1, U2, and we will define as U1 square plus U2 square. So what can I say about V at 0, 0 at origin? What is the value of V at 0, 0? What is the value at 0, 0?
0.
Is 0. 0 square plus 0 square means 0. And what about other points? At other points except 0, this must be strictly greater than 0. Whatever may be point, plus, minus, whatever may be the point, because it is square. So we will get V at U1, U2 is strictly greater than 0. Otherwise means that is whenever U1, U2 is not equal to 0, 0. Okay. And what extra condition? What is Liapunov function? We will go to the definition of Liapunov function. What is V at V is equal to 0 we want to show, and V at U is strictly greater than 0 for U not equal to V. These two conditions already we have shown. Now we want to show this. There exists a ball in which delta T of that VU which satisfies this condition is less than or equal to 0. If it satisfies, then we can say that it is a Liapunov function. Okay, so find that. And what is delta T at VU? V at FU. What is FU? Minus V at U. So what is V at FU here? Function V at, what is my FU for this? F at U is nothing but this one, or I can write here only. What is this? Cos of theta, sin theta, minus sin theta, cos theta, and U is nothing but my U1, U2, right? 2 by 2 matrix. So what will be this? Cos theta, U1 cos theta plus U2 sin theta and minus U1 sin theta plus U2 cos theta. This is the vector, right? This is my F at U. So F at U, I will directly write U1 cos theta plus U2 sin theta minus U1 sin theta plus U2 cos theta and minus V at U. What is V at U? V at U1, U2. So what is V at now? What is V at U1, U2? U1 square plus U2 square. So what is V at this matrix? Instead of matrix, it is a vector. What is V at U1, U2? First coordinate square plus second coordinate square. So U1 cos theta plus U2 sin theta bracket square plus minus U1 sin theta U1 sin theta plus U2 cos theta and its bracket square. That is my V at this. And what is minus V at U1, U2? V at U1, U2 is U1 square plus U2 square. Is that right? Now we can find this u1 square cos square theta plus u2 square sin square theta plus 2 times u1 u2 sin theta cos theta plus shall I write here only? Yes. U1 square sin square theta plus u2 square cos square theta plus minus times u1 u2 sin theta cos theta minus u1 square minus u2 square. So if I what will remain? U1 square cos square theta, u1 square sin square theta. So if I take u1 square common, cos square theta plus sin square will be 1, right? So and here u2 square sin square theta, u2 square cos square theta. Again I will get, so from these 4 quantities I will get u1 square plus u2 square, and this is 2u1 sin theta cos theta, here minus 2u1 u2 sin theta cos theta. So these 2 will get cancelled, right? And these 2 also will get cancelled. So what will remain?
0.
It will be
0.
right? So V at delta t, V at u is equal to 0, means it is less than or equal to 0. So consequently, capital V is a Liapunov function. It is not a strict Liapunov function. It is just a Liapunov function. Function at origin. Origin means 0, 0, origin, and hence origin is a stable. Origin must be stable by theorem 4.18. Origin must be, hence by theorem 4.18 origin must be stable. Is that okay? In this example we want to show origin is stable, so we have defined one Liapunov function. This function V at u1 u2 u1 square plus u2 square, and which satisfies the all that 3 conditions of Liapunov function. Okay, V at 0, 0 is 0, and V at other points it is strictly greater than 0, and delta t V at u is less than or equal to 0. So V is a Liapunov function, and hence origin must be stable. Is that okay?
Yes,
So we will go to example 2, second example. What can be said about the stability of origin, about the stability of origin for the equation u at t plus 1 is equal to u2t minus u2t u1 square t plus u2 square t u1t minus u1t u1 square t plus u2 square t. This is my f of ut. So again we need to check whether there again we will define the same Liapunov function, and we will check whether it satisfies the property. Okay. So again define the same Liapunov function. Define V at u1 u2 is equal to u1 square plus u2 square, and we know that origin only, no, we want to show this. Then v at 0 0 is again 0, and v at u1 u2 is strictly greater than 0 when u1 u2 is not equal to 0 0. Right, now only we need to check delta t vu. Consider delta t v at u. It is defined by v at fu minus v at u. So what is v at fu? V at that matrix u2t minus u2t u1 square t plus u2 square t, and here second coordinate is u1t minus u1t u1 square t plus u2 square t minus v at u1 u2. So what is v at fu? Again first coordinate square plus second coordinate square, right? So what is first coordinate square now? u2t, I can write this as 1 minus u1 square t plus u2 square t and its square plus u1t 1 minus u1 square t plus u2 square t brackets square, and minus what is this, u1 square minus u2 square, or you can write u1 square plus u2 square. If we simplify this, what we will get? Which is equal to u2, instead of t I am writing just u2 square plus u1 square. You can check this, 1 minus 2 times u1 square plus u2 square plus 1 square plus u2 square and its bracket square minus u1 square minus u2 square. And if I again simplify, this will be u2 square plus u1 square 1 minus its bracket square, we will have bracket square. Simplify this, minus 2 times plus u1 square plus u2 square. Okay, check this. u1 square plus u2 square we can have common from here, and it will have minus 2 plus u1 square plus u2 square. Can you get this? You can simplify this latter also, okay, and check. You will get u2 square plus u1 square bracket square minus 2 times plus u1 square plus u2 square. Now this is strictly less than 0 if u belongs to v of 0 root 2. This is 0 0 root 2. Okay, and u not equal to 0. So because minus 2 plus u1 square plus u2 square, if we take any point in this ball centered at origin, radius root 2, then we can have this delta t must be strictly less than 0. So we can say that v is a strict Liapunov function. And the origin, and hence the origin is asymptotically stable. The origin is asymptotically stable. In this case, it is asymptotically stable. Also, since delta t v at u is strictly less than 0 is equivalent to mod of fu is strictly less than mod u. So by corollary, second corollary 4.2, every solution originating in B, what is that B? Centered at 0, radius 2, must converge the origin. And this completes our Liapunov function. Is that okay?
Yes, ma'am.
So now only one section is remaining, Floquet theory. Tomorrow and after tomorrow there won't be a lecture. So Monday we will start that Floquet theory. Okay. So is this clear? Liapunov function. So go through it. If you are having any doubts, again you can ask me on Monday, or you can ask me on WhatsApp also. So we will stop here today. And one more thing is your internal, I think somebody shared you that anybody shared that timetable?
No, ma'am.
So